seriously. They tried to figure out what we had done wrong. This is February of 98. By the end of 1998, no one had found anything obvious that we had done wrong. So the editors of Science magazine proclaimed this to be the top scientific breakthrough of the year in all areas of science, which pleased us. We still weren't sure, but no one had proved us wrong, at least in that calendar year. The caricature of Einstein is surprised here, not because he's blowing multiple universes out of his pipe. You might not have known that there are multiple universes and they come from the pipes of theoretical physicists. Well, the first part of that statement might be true. Come back someday and tell you about it. But, he's surprised because this one universe is expanding progressively faster with time rather than more and more slowly. So it's not behaving the way a universe would work under the influence of normal gravity. He's doubly surprised because he has a sheaf of papers here with an equation. Lambda equals 8 pi g, Newton's constant, times the density of the vacuum. Now you might say, why did Peter invite this bozo from Berkeley? You know, the density of the vacuum, you were taught on your mother's knee that the vacuum is zero, zilch, nada. Well, first of all, it's not my idea, it's Einstein's idea. He's a lot smarter, okay? I'm just the messenger here. Secondly, the vacuum can have a non-zero energy density, it turns out. That was a brilliant idea that Einstein had. The idea was motivated by the following observation. The universe doesn't seem to be collapsing in on itself, and yet gravity pulls. So here are these two galaxies, Milky Way and some other galaxies, should be coming toward each other. At that time, 1917, Hubble had not yet discovered the expansion. Most physicists thought the universe is static. So Einstein reasoned that, well, there's got to be something counterbalancing this attractive force. May the net force be with you, right? Star Wars, they got it. The force may be with you, but if some other force is against you, you're going to lose. So all the physicists here know that the motto should have been, may the net force be with you. Here, if the net force is zero, the universe will be static, all right? Simple. So he introduced this idea to account for what people thought was a static universe. He didn't like the idea because it did imply that the vacuum not only has a non-zero density, but that it's a repulsive type of stuff. That was a repugnant idea. And moreover, it was a fudge factor. It's a constant of integration, but it had to be tuned to have exactly the same repulsive effect as the attractive effect of gravity. So it seemed ad hoc. It seemed kind of arbitrary. It was, yes, it's a constant of integration, but why should it have exactly the value that negates gravity? You know, didn't seem to make natural sense. So he never liked it, but he felt compelled to introduce it. A dozen years later, Hubble discovered the expansion of the universe, so the whole physical and philosophical basis for the cosmological constant vanished. Einstein renounced it as having been the biggest blunder of his career. He could have been famous had he not introduced it. He predicted that the universe is in some dynamic state. So here he is, sad that he ever introduced the idea. Now again, I don't know that that's what he's thinking, just like I don't know that Zwicky was thinking about the small brains of his Caltech colleagues when he was doing that thing, but he may well have been thinking that. He referred to it anecdotally as his biggest blunder. Okay, to George Gamow, who is known to have exaggerated some things, but nevertheless, Einstein is on record for not having liked the cosmological constant. Whether it was the biggest blunder, who knows? What have we done the better part of a century later? Well, we have reincarnated the idea, not to have a static universe, but one which on the largest scales, over 10 million light years or so, is repulsive. So here in this room, the down arrow dominates. In our solar system, down. In our galaxy, down. But as you get to 10 million light years and beyond, the up arrow dominates and you have an accelerating universe. Okay, that's the idea. So, going back to this diagram, instead of saying omega matter less than zero, we really don't know, didn't know, and still don't know of any substance with an actual negative gravity in the sense of GNM over d squared, stick in a negative m. We don't know of anything like that. But we can substitute this with lambda greater than zero. In other words, this goes back to Einstein's 1917 idea. We've resurrected it, something that he had renounced. So instead of being his biggest blunder, it could have been that this idea was in some ways his greatest intellectual triumph, that the vacuum itself may have a a non-zero energy density and that it may be a repulsive energy. So that's the idea. Einstein would be surprised if you were to see the data now. Just a few more things here. You might say, well, this is based on supernovae. There could be things wrong. As many of you, all of you know, I think the more important the scientific discovery, the greater is the burden of proof, right? You have to, in particular, verify it with completely independent techniques. I'm running out of time, so I won't go through these in great detail. But you can look at the afterglow of the Big Bang, the so-called cosmic microwave background radiation. Here it is. There are hot spots and cold spots. Analysis of those hot spots and cold spots provides independent evidence for the universe being permeated by what we now call dark energy. You can also watch the development of the growth of large-scale structure in the universe. These are galaxies and clusters of galaxies and superclusters of galaxies that form over cosmic time. This is redshift from these initial little density fluctuations. You just let gravity loose and it forms the universe, the cosmic structure. But if you don't include a repulsive component as well, the computer simulations don't give as good a match to the observations as they do if you include a repulsive component. So that's another piece of evidence. Here's the observed universe. It's a simulation of the observed universe, but it's based on the actual measured distribution of galaxies. And the point is that the computer simulations look like this if you include not only attractive, gravitationally attractive stuff, but repulsive stuff as well. So there's now a lot of evidence for it. It might not be the cosmological constant, the acceleration could be something else. So we call it more generically dark energy. We don't know that it's the vacuum energy of space. We don't know that it's the cosmological constant. It could be some sort of new energy permeating space, like these light waves, but not light waves. There's a subtle difference between energy permeating space and being a property of space itself. That's the idea. Studies have shown that averaged over giant distances, 1 billion light years, dark energy is the dominant component of the universe, and we don't really know what it is. The exotic dark matter, non-baryonic, that is non-protons, not neutrons, not atoms, basically, 25%, we don't really know what that is. The stuff we know of pretty well is a relatively minor slice of the pie. Pretty amazing, actually. So this physical origin of dark energy is a huge mystery, probably the most important observation-motivated problem in all of physics today. It's 70% of the universe. We better understand what it is. And it provides clues to the holy grail in theoretical physics, and that would be a unification of quantum physics and gravity, a quantum gravity of theory. It's what a quantum theory of gravity. It's universally thought that whatever this stuff is, it's acting on the quantum level, but everywhere, okay? And so any quantum theory of gravity, any version of string theory that does not account for it can be rejected as not being a viable theory. So it's very important stuff, and that's why by 2011, when it was verified in many, many other ways, it was recognized with the Nobel Prize to the team leaders, Saul Perlmutter at Berkeley, Brian Schmidt in Australia, and I'm happy to say that for the third person, they can only really give it to 3, they chose Adam Rees, my postdoc, who was the first on Schmidt's team to recognize the result. And this year's Nobel is even a more egregious example of this. There were 50 of us working pretty hard. Well, the LIGO detections, and Kip Thorne, our own Kip Thorne, got the Nobel Prize. There were 1,000 people on that discovery paper, but Barry Barish and Kip Thorne and Ray Weiss got the Nobel Prize, and hats off to them. But there were a lot of people who worked really, really hard without whom the measurement would not have been made. And they well recognize that. Anyone who wins the Nobel Prize for what is a team effort almost always is humble and says, look, I wouldn't have done this without all the others working as well. So, and Kip and Barry did that as well, both Caltech professors of physics. So they realized that without the rest of us working in the trenches, they wouldn't have been honored in this way. And so they actually brought us over to participate in Nobel Week, which was really fun. They spent a good fraction of their prize money. We got to go to the ceremony. We're up here in a balcony somewhere there. The King of Sweden was there. Anyway, we got together right after the award of the gold medal of the prize to Schmidt and Rees. And the other team, Saul's team, is here, and I should be in this photograph, but I couldn't make a clone of myself or a quantum entangled particle. I, at that moment, was with the primary team with which I was associated, Reese and Schmidt. We were having a celebratory lunch, just reminiscing about what it was that we did and how we did it. And at that lunch, my wife Noelle revealed a consolation prize for all of us who did not technically win the Nobel Prize. And that consolation prize was a limited edition t-shirt, Dark Energy is the New Black. And it's limited edition, and she sent one along with a $2 bill to the King of Sweden saying, here are 2 items you don't probably already have. Definitely not this, and probably not the US $2 bill. But anyway, that was kind of fun. A few years ago, the Breakthrough Foundation recognized all 50 people with a share of the Breakthrough Prize in Fundamental Physics. But to me, really, the prize was working on this and contributing in an important way to a really fundamentally new understanding of our universe. How will the universe end? This was a Time magazine cover in 2001 about our work. Well, at that time we thought we knew, but, and the answer was, well, if you want to look at galaxies like this with your very own eyes, you'd better do it pretty soon, because the galaxies will be whisked away within a few tens of billions of years to such great distances that you won't be able to see them, right? A runaway universe. But we now understand that since we don't know what the dark energy is, there's a chance that its sign will change in the future, right? We don't know what it is. If it's the cosmological constant, it'll be a runaway universe. But if it's not the cosmological constant, then there's the possibility that it'll, reverse sign and end up in a big crunch after all, or a gnab-gib. Or it could be that it'll become even stronger, and eventually everything, including you and the atoms in which you were made, will get ripped apart. So this runaway universe with constant dark energy, which is what we thought in 2001, is not necessarily the answer. The data are consistent with a constant dark energy, but do not exclude either of these possibilities. So if you'll permit me 3 minutes, our latest work has been to try to measure more accurately this past history to try to figure out which of these futures will actually be the one that the universe goes through. And we do have a surprising result. And that is that the current rate of expansion seems to be higher than expected, even when you take into account this accelerating expansion. And the idea is the following. The microwave background people measured the early universe. This is a snapshot of the universe when it was 380,000 years old. That, plus the standard model, where the dark energy is the cosmological constant, leads to a prediction of the current expansion rate of the universe, the current Hubble constant. So they predict the current expansion rate. They get a number, 66.53 plus or minus 0.62. Okay, pretty small uncertainty. Kiloliters per second per megaparsec. Okay, we measure, direct measurements gave a value of 70 to 75 plus or minus 4 to 7. So it differs, but not in a statistically meaningful way, right? And error bars easily overlap. So no one really took much notice of this apparent discrepancy. What we have done recently is we've greatly decreased the error bars here and our confidence in the number. And we did this by using the Hubble Space Telescope to measure the distances of galaxies more precisely than before in which type 1a supernovae occurred. And here's one such galaxy, and we basically measured Cepheid variables. So we've gone all the way back to Hubble's technique and Henrietta Leavitt's technique. And we did this really, really well, we think. We think we did it really well. And so here's what we recently published. We get Hubble's constant to be 73.24 plus or minus 1.74. Recall the microwave background result, 67.8 plus or minus 0.9, or 66.93 plus or minus 0.62. It depends on which of their analyses you prefer. But in any case, this is roughly 3 standard deviations from our result. That's not a discovery. In particle physics, you need 5 sigma, okay, like something like the Higgs. But we've got one universe and a limited number of type 1a supernovae, and if you wait till 5 sigma, you'll never publish anything, okay? So we published this, we said, look, here's our best estimate right now, take it or leave it, try to find out where we went wrong, but formally, 3 sigma should only happen by chance 1% of the time. So this looks like it might be something interesting. When we first announced the accelerating universe, it was no better than 3 sigma, and hey, we were right on that. So we've got a pretty good track record, okay? So there may be a conflict, is the point. We have smaller uncertainties than before, and we think we understand them very well. So, stay tuned. The possible explanations are very interesting. One or both teams might be wrong. That's the least interesting explanation, but it's possible. If neither team is wrong, then general relativity might be wrong. Despite the merging black holes and neutron stars that LIGO has detected, that's again small-scale, strong field relativity. It could be that large-scale, weak field, universal relativity could be wrong. I don't think so. I think relativity is really on strong footing, but hey, scientist has to be open to all possibilities. More likely, dark matter is behaving weirdly. It's interacting with the universe in ways that we thought before that it shouldn't. Maybe dark energy is becoming stronger. Maybe we're on our way to a big rip. I think there's other evidence that argues against that, but it's possible. And then my favorite explanation is that there's a new, very light, fundamental subatomic particle, a neutrino, that does not participate in what we call Big Bang nucleosynthesis, the synthesis of the lightest elements, because for that, we know that there are only 3 neutrinos. So it's got to be something like a sterile neutrino, a neutrino that exists but does not interact with other things very much, and that's why laboratory physicists haven't found it either. Admittedly, a bit of a long shot, but it wouldn't be the first time that a discovery in astrophysics has influenced fundamental particle physics. So, we call this dark radiation. That's my favorite so far, but time will tell. Stay tuned, basically. It's a very exciting field. As I say, I've been privileged to work in it. I've been just astonished by the results, and Robert Frost could not have known about these results. In fact, he didn't even know any cosmology in 1923 when he wrote his famous poem, Fire and Ice. But it's remarkably appropriate, given what I just told you about. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, Frost would prefer the big crunch universe, the one that ends in fire, a passionate, hot universe. But if the universe and he had to perish twice, eternal expansion and an ending in ice would be okay with him, and that's perhaps appropriate given his name, Robert Frost. So it's just interesting that his poem is so relevant now. Anyway, I've been supported in many, many ways, National Science Foundation, NASA, various private donors to whom I'm very grateful. Some are even in this room, interestingly. Wayne Rosing, a Google guy who now has built a network of telescopes all over the place. Very, very grateful to them. I'm also grateful for having been privileged to use these incredible machines. The Hubble Space Telescope, I'm looking forward to the James Webb, which will be launched, we think, now in spring of 2019. It's been delayed a little bit. This has been a wonderful instrument to use. The Keck telescopes have been just, incredible, out of this world. And I want to give a particular shout out to the University of California's Lick Observatory, because that, as I said, is where our students really get to learn, get their hands dirty with research, make mistakes, not just be my apprentice, but actually do projects of their own from start to finish. They start with an apprenticeship, but then they learn enough to do a project on their own, and that's where the real learning, that's where the real leadership is developed. With these relatively small telescopes by today's standards, to which we have frequent access. Students have access, and we can follow a supernova's evolution and find exoplanets. I didn't have time to talk about that. But repetitive access to the same relatively small telescopes is complementary to just having a small amount of time on the world's biggest machines. I love the world's biggest machines, but I get that much time. If I'm lucky, I'll get half a night a year on the 30-meter telescope. I favor the 30-meter. I want it to be built. But if I even get that half a night a year and it's cloudy, that's not something around which I can build a research program and train students, right? That's where we do it. And I'm president of an organization called the Lick Observatory Council, which runs the Friends of Lick Observatory. You can look it up if you wish, and I encourage you to become a friend. There are various perks associated with it. I also was able to get Google to make a significant contribution to Lick Observatory, $500,000 a year for 3 years. Well, I'm hoping this was just the courtship phase of what will end up being a long relationship. You will notice that 3 years plus December of 2014 was December of 2017. I am awaiting their decision. One of the, and I give them updates every once in a while, but one of their criteria was, how well will I be able to leverage their contribution in terms of being able to attract private donations. And we've been raising matching private donations, and I'm very grateful to those who have contributed. If you'd like to contribute, just go to give.berkeley.edu, put Lick in the search box, or Google Give to Cal or something, and it'll take you to the UC Berkeley Lick Observatory Operations Fund. I might point out that you would be indirectly supporting Caltech as well. And that's because at the 48-inch Schmidt telescope, my colleague Sri Kulkarni has been running an amazing thing called the Palomar Transient Factory. They found lots and lots of exploding stars. They're now transitioning to a bigger device called the Zwicky Transient Facility. They're going to find hundreds, if not thousands, of things that go bump in the night, okay? Thousands per year. And they're just starting in the next couple of months. The Zwicky Transient Facility with the old telescope that Hubble used. It's equipped with a CCD array that covers 40 square degrees. They're going to go boom, 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 boom throughout the night. And then the next night, same fields, boom, 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 boom. Find out what goes bump in the night. And then they're going to call me and say, hey, Alex, can you use your facilities at Lick to do follow-up work with your students on the objects that we discover? And so we're still quite close collaborators. But by helping out Lick Observatory, I realize it's not technically a Caltech facility, but you would be indirectly helping Caltech as well. So thank you for the opportunity to speak with you, to such a distinguished audience, and to show you some flavor of the excitement of modern cosmology and my enthusiasm for working in this field. Thank you so much.